I talk a lot about preparing for analysis qualifying exams in the recent videos because that's what's on my mind recently. But the real analysis portion is just the first half. There's a second half that you need to prepare for. But luckily, it's only one semester's worth of material. So what exactly do they expect you to do on the complex analysis portion? The complex analysis portion is typically easier, thankfully. And depending on who writes it, you'll either have a really good time or a really bad time. So let's talk about what to expect. So there's 5 questions, and the first question again is a theorem, some theorem from the course. The second problem is a contour integral. So they give you a contour in the complex plane, they give you a complex function, and they ask you to find the integral. So it's like calculus, but on the complex plane. And then the third problem is a conformal map, where they give you a region in the plane, and they give you a second region in the plane, and they ask you to find a map, a conformal map, that takes you from one to the other. It's the most puzzly of the problems. It's probably my favorite part of complex analysis is constructing that puzzle, because it feels less like math and more, just like a puzzle, which is is like my favorite part about math classes is not doing math. It even seems kind of strange to say that. And the last 2 are just some questions. There's not really a pattern to them. They can ask whatever they want. But it's generally agreed upon the first 3 questions are like whatever in there. As a result, it's a lot easier to prepare for the complex analysis portion because there's only one semester's worth of stuff and you have a more general idea of what they're going to ask for. And I don't know why I wrote a 5 where there should be a 3 here. That's kind of weird. That 3 should come before number 4 and after 2, right? So those are the 5 questions. And just like the real analysis portion, I have a big thick stack of problems I've done. So I believe these are the old problems that I did. Yeah, these are the old ones. So I'm currently rewriting these so that I'm creating a new stack of study material. And let me think, is this an old one? Yeah, these are old. This whole stack is old. So let me show you the new stack I've been working on. It's right here. This is the first homework packet, so potentially there's a qualifying exam problem in this packet. So you can see just what types of homework problems we're being asked to do. Now it said on the top that it was due January the 31st. I am not registered for this course. I'm just sitting in on it, and the guy gives me the homework package just because I'm there. I'm not actually taking the class, so I don't really have to turn it in. So I just do the problems at my leisure. Let's see here. This is homework packet 2. Some of these problems are quite nice, like this one, 21, 20. Every compact set is complete. Pretty simple problems. And he gave us a 3rd packet recently. Haven't even really looked at it. When I get, I'm taking other classes at the time, so I'll get to it when I get to it. All right, so now we have this stack, which includes the theorems. So there are going to be fewer theorems because it's only one semester's worth, and I'm a bit scared that I missed some theorems. But there should be 45 theorems here, so there's a lot. Let me see, where does it end? Where does it end? When does it end is a better question, right? Whatever, this is good enough. So those are the theorems you can see. Really kind of just looks like my other stack of real analysis problems. And I choose this one to show you in particularly because I do have my favorite theorems from both real and complex, and this one's my favorite from complex analysis. It says that if you have an open region omega in the complex plane and you have a triangle inside such that the boundary of the triangle is completely contained within omega, the interior, I didn't really write that, but I should have written that. It's the interior of omega. Then you know that the integral of fz over the triangle T, where f is a holomorphic function, is going to be equal to 0. And it's used to prove a more general result. So if you just have omega, and you have a curve inside omega, and you integrate along that curve, and your function is holomorphic, or analytic in omega, then no matter what curve you pick, your integral is always going to be 0. And the reason it's my favorite is because the result sounds too good to be true. But if you think about it a little bit, it kind of makes sense why it would be 0. So it's my favorite. I like the name of it too, Cauchy-Goursat. I like drawing the pictures. I always like to draw. There are different versions of this theorem, but I think if he's going to ask us to prove something on a test, then the triangle one is the one he's going to ask, because that's the way I remember him doing it in class. I also got it from the Stein-Chikarchi book. So that is the theorems that I need to study. And then I need to do, I haven't finished yet. I'm still in the process of making these notes. But the next ones are going to be my conformal maps. The conformal maps are my favorite, as I mentioned earlier. Turning stuff into other shapes. So you can just see what kind of pictures we're dealing with here. These pictures are how we did it in his class, so that's what I'm used to presenting them. You just take, if you have multiple steps, you just take the compositions of them. He kind of understands what you mean. Just hold my camera steady. This one was fun. I did this one in class up at the board. And that was the procedure I took. I think I'm going to try and get at least 100 of these. 100 of these done before I move on. I think I'm on 20 now. I stopped at 20. So I need to do 80 more. And then when I'm done with that, I'm going to do 100 contour integrals. There's an old stack somewhere around here where I did contour integrals the first time. So I'm going to do 100 of those. So I got 45 theorems, which I'm calling 50. I'm going to get 100 conformal maps, 100 contour integrals. And then the other 100, I'm going to do previous qualifying exam problems and just try and come up with something, I guess. Just to see if I can, you know, get those practice problems in, because I can't really afford to do bad on the complex portion. It's the most important one. By most important, it's where most of your points are coming from, because it's the most predictable. So anyway, that's complex analysis. Thought I'd talk about it a little bit. A little bit of a short video, but I thought it was necessary to speak of this. Also, by the way, ignore this argument that's on the screen for C being complete. I think I just wrote some nonsense down. I had the general idea of what to do, but I'm kind of embarrassed to show it. So let me show you a theorem I'm less embarrassed to show. Here, this one I copied from a book. So you can get mad at the book instead of me. Okay, I think that's good enough for one video, so stay tuned for more updates from the PhD life.